What is the second law of thermodynamics? Well, it's the law that states that entropy in a closed system tends to increase. And you might know that the universe is considered a closed system, so the entropy in the universe tends to increase. Now, when asked what is entropy, you might have heard that it's a measure of disorder. When you ask what is disorder, your professor might say something about you having a messy bedroom or something along those lines, but that's about it. And that just doesn't tell us much. So here's a much better definition of entropy. Entropy is the spreading out of energy. What do I mean by this? We'll consider this thought experiment. We have two blocks, block A and block B. And these blocks are the same material, same volume, same everything. The difference is that block A is heated to 100 degrees Celsius, block B is chilled to 0. When we bring these two blocks in contact with each other, what's going to happen? Well, you might intuitively know that heat energy goes from hot to cold. So these two blocks will equalize somewhere around 50 degrees Celsius, right? What you'll never see is block B getting greedy and asking for more energy, or block A refusing to share. It will always equalize at 50 degrees Celsius. And this is what I mean by the spreading out of energy. The energy will always spread out among the two blocks. But why is this true? Why is the second law of thermodynamics true? To answer this question, we're going to zoom in to where these two blocks meet, and we're going to look at an atomic scale, right? So here we have drawn 5 atoms. Atoms 1 through 4 exist right on the edge of the hot block, and atom number 5 exists right on the edge of the cold block. And we're going to make 4 assumptions about these atoms. Assumption number 1, atoms 1 through 5 are the same element. Doesn't matter what element it is, we're going to assume that they're the same. So same charge, same mass. Assumption number 2, we can ignore all interactions outside atoms 1 through 5. So all the other atoms in these blocks can be ignored. Assumption 3, atoms 2 through 5 are equidistant from atom 1. Assumption 4, heat energy is quantized. Now what does this one mean? Well, it means that these atoms can have 1 heat, 2 heat, 3 heat, they can't have half heat. And if an atom has 1 heat, they can give that 1 heat to only one other atom. Can't split it. For our case, we're going to say that atom 1 has 1 packet of heat energy, and atoms 2 through 5 have none. But what is heat energy? Well, as the GOAT Richard Feynman so eloquently puts it, it's the jiggling of atoms. Right? So atom 1 is jiggling a decent amount, and 2 through 5 are not jiggling, or at least not a lot. Atom 1 wants to give its heat energy to one of the other atoms nearby. How does it do this? To understand how it does this, we need to know, how do matter particles actually interact with each other, communicate with each other? And they have 4 ways of doing this. Right? We have 4 fundamental forces of nature, 3 if you've had a decent amount of Red Bull. And there's one in particular that matters to us here, and that's the electromagnetic force. For us, this is going to manifest as the electrostatic repulsion between the atoms. Now we have a formula to help us calculate the strength of this repulsion. That's Coulomb's law. So for 2 charged particles separated by some distance r, the electrostatic force between them is equal to Coulomb's constant times the charge on particle 1, the charge on particle 2 divided by the distance of separation squared. How does that apply for us? Well, we need to figure out what the strength of all these labeled forces here are. This is going to tell us the extent to which they're all communicating with each other. They're all asking for that heat energy. What were the assumptions we made? Atoms 1 through 5 are the same element. So 2, 3, 4, 5, they all have the same charge. Atom 1 has the same charge. So Q1 and Q2 is the same for all 4 cases. And we also said that these atoms are equidistant from each other. So R is the same for all these 4 cases. And Coulomb's constant is just a constant, it's the same for every case, right? So all 4 of these atoms are begging for that heat energy, and they're all equally persuasive. So how does atom 1 decide who to give it to? It just doesn't know, right? So it just picks at random. It says eeny, meeny, miny, mo. What does that mean? That means that all 4 of these surrounding atoms have an equal chance of getting that heat energy. They've all got a 25% chance. But look at this. 3 of these atoms exist in the hot block. Only 1 exists in the cold block. So there's only a 25% chance that the heat of atom 1 gets transferred over to the cold block. There's a 75% chance that the heat stays in the hot block. Now you're thinking, what the hell? You said we were going to develop some intuition as to why heat flows from hot to cold. Not only have you not given us that, but you've given us intuition as to why it should go the other way. And, maybe you want a refund, and I'm not going to give that to you. There are no refunds, but just humor me for one more thought experiment, and it will make sense. The sweater came off for this one. So here's the second setup. We've again got block A and block B. This time both of them are just made up of 9 atoms, represented by these squares. And block A has 6 packets of energies represented by these black dots. Block B currently has none. So there are some terms we need to define, and those terms are microstates and macrostates. A macrostate represents the overall state of a system. So for example, if we have 6 packets in A, none in B, that's one macrostate. 4 in A, 2 in B is another macrostate. But consider again having 6 in A and none in B. There's so many different ways that we can arrange the 6 in A, right? We could have all 6 in one atom. We could have them spread out among the top 2 rows. These are the microstates associated with the macrostate of having 6 in A and none in B. I know it's a little bit of a word salad, but hopefully that makes a little bit of sense. So what we need to do is calculate the number of microstates associated with this macrostate. And the way we're going to do that is, we're just going to count, right? So we could have 6 in this atom, that's 1. We could have 3 and 3, that's the second one. And I'm sorry, we're doing some math. Really, I am truly sorry, and trigger warning, I guess, but we're doing some math. We're going to be using this equation. This equation is going to let us calculate the number of microstates. And if you're curious where this equation comes from, you can go ask someone else. So the way this equation works is that Q represents the number of energy packets, and N represents the number of atoms that those energy packets are divided amongst. Right, so if all our energy packets are localized to block A, that means there are 9 atoms, so N is 9. So we do some voodoo math magic, right? We get 6, 9. The number of microstates for this macrostate is 3003. Right, so there are 3003 ways that these energy packets can be arranged such that we get 6 in A and none in B. Now 3003 is quite a bit, right? Not a small number. Depending on who you ask, I guess, but what happens when we bring the 2 blocks together? Well, now these energy packets can go from one block to another, right? They can go from one atom to another. And what we illustrated in the previous example is they really have no way of discriminating between the atoms in block B and the atoms in block A. So they're going to move across from block A to block B. And now N becomes 18, right? These six energy packets have 18 atoms that they can be divided amongst. So if we take Q as 6, N as 18, what does that number become? Take a guess. Put in your guesses right now. Maybe you thought it was twice as many. Maybe you thought it was 3 times as many. It's actually 100,947. So 100,947 is the number of microstates that correspond to having the energy spread out amongst block A and block B, right? 3 in A, 3 in B. I'm really not that good at math, all right? I'm really not. But what I do know is that this number is bigger than this one, right? I might even be so bold as to say it's a lot bigger than this one. I'm going to draw 2 alligators, because we need 2 alligators because of how big that number is. Now let's take a look at this graph that I drew here. On the x-axis, we have the number of packets in A. And on the y-axis, we have the number of microstates associated with that macrostate, right? So 0 on the x-axis means there are 0 packets in A, all 6 in B. 6 means there are 6 in A, none in B, and 3 means there are 3 in A, 3 in B. They're evenly distributed, right? What you notice is that we get a bell curve, a normal distribution. But we got 3003 possible arrangements where we get all the energy in block A, right? That doesn't seem like, it's definitely a lot less than 100,947, but it seems like it could happen. So why doesn't it happen? Well, consider that these blocks are incredibly simplified, right? 9 atoms. A real block of steel is going to have trillions of atoms. How does this bell curve change in that case? Well, it becomes a lot thinner. Maybe you can see where I'm about to go with this. There is no physical law that prevents heat from flowing cold to hot. There just isn't one, at least not that we've discovered. The fact that it doesn't, the fact that heat goes from hot to cold, the fact that entropy increases, the fact that the second law of thermodynamics is true is solely a matter of probability, statistics. It's just so immensely improbable that we would ever see it go the other way, and it just does that every time, right? Now, I like to imagine that maybe there's an alternate universe where they just get horrendously unlucky, and for them, heat always flows from cold to hot. I don't know that life could form in such a universe, but if somebody more knowledgeable is watching, I'd be curious to know what you think. I also think it would be really just incredibly hilarious if you went home today and poured yourself a beverage, put some ice in there, right? And the ice just started giving its heat to the drink. Your drink got hotter, the ice didn't melt, and you tried to tell people about it, and no one would ever believe you. Anyway, let's draw our attention to that equation in the corner. I'm betting you were hoping that I forgot about it. I've certainly tried. That's Boltzmann's entropy equation. All it tells us is that the entropy of a particular microstate is equal to Boltzmann's constant times the natural log of the number of microstates associated with that macrostate. The only reason I bring this up is just to show you the relationship between entropy and microstates. We've been talking about microstates, but not a whole lot about entropy, right? So there's the mathematical relationship between them. Now, the last thing I want to talk about is one of the most interesting predictions made by the second law, and that is that it predicts the end of the universe. Throughout this video, we've been talking about how energy spreads out, how entropy tends to increase, and why this all happens. But if entropy is always increasing, at a certain point, this should reach some sort of maximum, should it not? There should be a point of maximum entropy, of even spreading of energy across the entire universe. And this is one of the predictions made by the second law of thermodynamics. This is what's known as the heat death of the universe. At this point, all the energy is evenly spread out. There are no more energy differentials. Why does this matter? In order for work to flow, in order for something to happen, we need a difference in energy from point A to point B. Right? Think about circuits. They need a potential difference from each of the terminals, right? Bonds need a potential difference in order to form. The metabolic processes that happen in your cells need work to flow. So once we reach this point, none of that can ever happen again. Nothing interesting can ever happen again after this point. And you might be wondering, what can we do about this? And there's really nothing. This is just an inevitable end of the universe, but not to worry. We as a species will face a number of world-ending threats by the time we get to that point. We might even have GTA 7 by that point. I wouldn't count on that. I don't know if that brings you comfort. I don't think it really should, but it's just a thought. Anyway, thanks for watching.